All right, let's go over these problems. Today, we're going to mostly spend our time in chapter 14, especially looking at the reading examples. And I hope I can convince you by the end of class today that working with ideals in rings can actually be kind of fun, working with ideals and factor rings. So we're going to try to see if we can get to that point here. But in having you do problems 15 and 17, or at least think about them, I'm trying to emphasize a couple important facts. The facts in numbers 15 and 17 are pretty important to know. If you've got a ring R and A is an ideal in R, and the unity 1 happens to belong to A, then A actually has to be all of R. Not a proper subset of R, but equal to R. Any ideal that contains the unity has to be all of the ring. 17 says something similar. Any ideal that contains any unit at all, whether it's the unity or something else, has to actually be the entire ring as well. So ideals, while they are somewhat analogous to normal subgroups, they're not completely analogous. They do have some surprises, you might say, that don't show up with normal subgroups. So let's start by seeing if we can prove this. If A is an ideal of a ring R and 1 is in A, then A equals R. Well, certainly A is a subset of R. By definition of A being an ideal in R, it's got to be a subset. So the only question is R a subset of A? Is every element in the ring also in the ideal? Does that make sense? That's the only thing really that you have to do to show R is also a subset of A. Suppose you've got an arbitrary element of capital R. We must show that that element is also an A. Did you figure out the trick? Anybody want to share? Do you think you figured it out? It's based on the definition of an ideal. It's got to be. I mean, well, part of the hypothesis there. Did you figure it out? Anybody? Uh-huh.
Multiply 1 from A by R. It has to be in A.
Yep, exactly. Since 1 is in A and A is an ideal of R, remember I described the property at the end of class on Wednesday as the ideal being superclosed. It's more than just under multiplication, more than just closed under multiplication. I called it superclosed or ultra closed. I mean, these are just made up words. In the definition of an ideal, you got any element in the ideal, you multiply it by any element in the ring. The product has to be in the ideal. Therefore, R times 1 is in A. Since 1 is in A and R is an arbitrary element of the ring. A is superclosed, hyperclosed, whatever kind of made up word you want to use to emphasize that it's more than just multiply 2 elements of the ideal to get another element of the ideal. You multiply an element of the ideal times any element in the ring. It's also an element of the ideal. That's super important. That's the defining feature of ideals. But hey, R times 1 equals R. Done. Okay. So fairly easy to prove. pretty important actually as you work through the reading in chapter 14 and later chapters to know that if the unity is in an ideal, the ideal is actually not a proper ideal. It equals the entire ring. Again, number 17 is similar. If an ideal contains a unit, which would necessarily imply the ring contains a unity, then the ideal has to equal the whole ring as well. I'm not going to do a formal proof of that for sake of time, but just think about it here. So I is an ideal in R. By the way, I've never seen similar notation for normal subgroups used for ideals and rings. I mean, could we write this? Well, I suppose we could say we're going to use that notation here anyway to say I is an ideal. We'll go ahead and do it just for this class, but to tell you the truth, the author doesn't do it, and I've never seen any other professor do it. I don't know why not. Maybe because it's just too reminiscent of the symbol for normal subgroup. Meaning subrings, we don't use the less than sign either. We just say it's a subring. I don't know. Might as well use the notation, I think. I contains a unit. U is in I is a unit. What does it mean to be a unit? It means it's got a multiplicative inverse. But that's going to mean U inverse U is in I, since I is superclosed. Nothing about U inverse necessarily being in I, though it would be. But you don't have to use the assumption that U inverse is in I. You can say, hey, I've got something in I, U, times something in the ring, which does exist because I'm assuming U is a unit. Therefore, the product's got to be in I, but hey, that product is the unity, 1. Now apply number 15. One is in the ideal, therefore the ideal equals the entire ring. You could finish the proof without invoking number 15 as well. You could think of an arbitrary ring element as this product and still use the fact that I is superclosed. Okay. So anytime an ideal contains 1, it is the entire ring. Anytime an ideal contains a unit, it's the entire ring. Does that mean ideals are uninteresting? No, there's plenty of interesting ideals still to think about that are proper ideals, not the entire ring. All right, so again, I wanted to focus on the examples of reading of chapter 14 because they really emphasize some pretty important things that you should be able to do. And they are, when you really get into the calculations, especially examples 10, 11, and 12 on pages 252 and 253, they actually get kind of fun, maybe. I think they're fun, at least. And I want to try to convince you to think they're fun. But the first example we should look at is example 3. Let R be a commutative ring with unity, and let A be a ring element. Hey, looks like a cyclic subgroup generated by A. But no, it's not. In ring theory, this does not refer to the cyclic subgroup generated by A. Instead, it's called the principal ideal generated by A. Its definition is different. And in fact, if you were thinking about defining a cyclic subgroup in a ring generated by an element, which you could do, think about it here. Let R be a ring and let A be an element of R. I could still construct the cyclic subgroup generated by A if I ignore the multiplication in the ring. It's a group under addition, so I could still consider the cyclic subgroup generated by A under addition. I'm not going to use the same notation, however. So what notation should I use? I'll just use words. then the cyclic subgroup of R generated by A, I'm going to avoid the principal ideal notation because it means something different in ring theory, would be, since the group operation is addition, this would be not all possible powers of A, but all possible multiples of A, integer multiples. NA, where N is an integer here. A is not necessarily an integer. R is an arbitrary ring. This is not a product in the ring. N times A, I mean, I can say N times A, but it doesn't mean N times A in the ring. It means the integer N times the ring element A, which really means if N is positive, it means A added to itself with N terms, N summands. Right, we talked about this a lot before, back in chapter 3 even. If N equals 0, then NA equals 0. And if N is negative, NA really means negative N times the additive inverse of A, and negative N would be positive. So this really means negative A added to itself with N summands. I should say negative N summands, because negative N would be a positive number, positive integer. That would be the cyclic subgroup generated by A if you ignore the multiplication, only focus on the addition. And it's not necessarily the same as the principal ideal generated by A, because the definition of the principal ideal generated by A shorthand PID, principal ideal generated by A, is the set of all products R times A as R varies over the entire ring. And we are only considering this in the case where the ring is commutative. This would be the same as this. We assume R is commutative here under multiplication. Remember, that always means under multiplication, because it's always commutative under addition as part of the definition of a ring. The question is whether the multiplication is commutative or not. In example 3, we're saying we're just going to consider the simple case where R is commutative. You could consider ideals generated in non-commutative rings, though they would be technically what are called left ideals or right ideals. When we think about principal ideal domains, we're going to think about commutative rings, which in a sense is unfortunate because that also would rule out thinking about matrix rings here. And matrix rings could be interesting sometimes. Although that is one of the examples, think about a matrix ring. Evidently, yeah, the ideal is defined in such a way that this equality is true anyway. And so we can still talk about principal ideals in that context, and we can still think about factor rings. But initially, at least in example 3, with principal ideals, they're saying let R be commutative. I guess the other examples that we're going to look at is not really a principal ideal. These are still analogous, however, to cyclic subgroups in the sense that they are, you might say, the simplest kinds of ideals, whereas cyclic subgroups are the simplest kinds of subgroups. Is this really an ideal of R? We'd have to prove it with the ideal test. First of all, is it non-empty? Well, that's obvious because R can be anything in the ring. Is it closed under subtraction, and is it closed under, or super closed under multiplication, I should say? Not going to prove it, but let's think about the idea of the proof. Is it certainly non-empty? Because again, R can be anything in the ring, and A is a fixed element of the ring as well. This is not the word A, this is the element A. Is it closed under subtraction? Give me two elements of that form. When I subtract them, do I get something of that form? Sure. Use the distributive property. There we go. That does it. Is it superclosed? Give me some arbitrary element of the ring, call it, say, S. Multiply it by something in this principal ideal domain, an arbitrary element of it. Is it still in the principal ideal domain? Yeah, the associative property can be used to emphasize that it is something in the ring times A. This is an element of the principal ideal generated by A. Okay. This is going to play a really important role for us. But these are not the only kind of ideals you can make. These are just the simplest kinds of ideals besides the trivial ideal. Let's get into examples 10, 11, and 12 now. And try to have some fun, a mathematician's idea of fun. All right, so here we have a matrix ring, R, 2x2 matrices with integer entries. Symbolically, we could say in example 12, example 10, that R is, excuse me, M2Z. The 2 stands for 2x2 matrices. The Z stands for integer entries. Let I be the subset of R consisting of matrices with even entries. It's a subset here initially. If we wanted to write it out without words, and instead use symbols, I is the set of all matrices, say of this form, where those B's are all in 2Z. By the way, I should mention with principal ideals, I was going to mention this, but forgot. With principal ideals, I said how it's different than the cyclic subgroup generated by the element in general. However, in the integers, they're the same. A side comment here. In the integers, Z you got an element of Z. The cyclic subgroup generated by that element and the principal ideal generated by that element are the same when the ring is Z. In general, they're different, but for Z, they're the same. When you compare this set with this set, when the ring is Z, well, R would be from Z in there. And the ring multiplication in Z is the same as this kind of multiplication in general. So I forgot to mention that. I'll probably re-emphasize it at some point. So initially, this is just a subset of that subset of R. But the claim in example 10 is that it's an ideal. It's pretty easy to prove. Let's just think about it. I won't even write anything down. Is it closed under subtraction? You subtract two matrices of this form, all of whose entries are even numbers, you're going to get a matrix whose entries are even numbers, right? You subtract any two even numbers, it's still going to be even. It's also superclosed under multiplication. You multiply this by any matrix. Whether that matrix has odd numbers or not, you're going to get a matrix with even numbers. Because an odd number times an even number is still an even number. And the sum of any two even numbers is even. Does that make sense? Can you just imagine doing the argument? This is an ideal of R. Ideals are always, as subgroups under addition, they're always normal subgroups. In fact, subrings that are not ideals are also normal subgroups. And so you could always form the factor group even with a subring, not necessarily an ideal. However, the superclosed nature of ideals is necessary to construct the factor ring and make multiplication in the factor ring well defined. That's what the definition of an ideal is for, is to make coset multiplication well defined, not just coset addition. Why would even a subring be a normal subgroup of the ring if you only consider addition? That's because the ring is commutative under addition. And in any group that's abelian, any subgroup's automatically going to be normal because the group is abelian. Anyway, coming back to this example. So it's an ideal. I is an ideal in R. I think I will typically do the same thing that the book does and not use the normal subgroup notation here. It won't bother me if you do it on your homework. I is an ideal of R. We just argued that verbally. So R mod I is a factor ring with a well-defined multiplication. I could always form R mod I as a factor group under addition, because again, I will automatically be a normal subgroup of R under addition, whether it's an ideal or not, if it's just a subring. But if it's also an ideal, if it's superclosed, then multiplication in the factor ring will be well defined and it will be a ring itself. It's a factor, not just a factor group, but a factor ring. But then the book asks, what are the elements of this factor ring? The claim is it's only got 16 elements. In fact, furthermore, though they take this form, notice these are cosets. Cosets don't go away. They'll always be with us for the rest of the semester. Cosets with an addition notation because we emphasize that the group operation is addition. Where these R's are either zeros or ones. So in each entry, there's two choices for one of those are 0 or 1. And so the total number of cosets you can make is 2 times 2 times 2 times 2, 2 to the fourth, or 16 possible cosets. The author doesn't prove that here, but does an example to illustrate how you would argue the general case. And here's the key calculation. Take an arbitrary coset with an arbitrary 2 by 2 matrix from R in here as the coset representative. Not all zeros and ones. You'd like to figure out how can I write this coset in this form where all the entries are zeros or ones? That's the goal. And the trick is, based on the fact that I consists of matrices with even entries, is to rewrite this matrix as the sum of two matrices, where this one has just zeros or ones, and this one has all even entries. And you can always do that. Then, because this one has all even entries, and because I is superclosed, it's like it gets sucked into I. I even like making a sucking sound in my mind. Gets sucked into I. What fun. This is the fun part. Fun. A mathematician's idea of fun. And you can rewrite the ideal this way. Now, you should be looking at this and saying, well, did we really fully justify that it can get sucked in? Or that it does get sucked in? I mean, how would you fully verify this? Well, it's really based on what it means for two cosets to be equal to each other. In group theory, factor groups, we said two cosets were equal, AH equals BH, if and only if A inverse B is an H, which is also equivalent to saying B inverse A is an H. Remember that? This also applies to a special case when B is the multiplicative identity E. AH equals H, in fact, if and only if A itself is an H, which is also equivalent to A inverse being an H, when H is a subgroup of G. This was true even if H is not necessarily a normal subgroup. You could still talk about these cosets in this way, though you wouldn't talk about factor groups if H was not a normal subgroup. In ring theory, where we're thinking about factor rings, we use additive notation. A plus H equals B plus H. If and only if, what's the corresponding facts with additive notation? If and only if B minus A is an H, which is true if and only if A minus B is an H. Since the group operation is addition, where of course B minus A really means B plus the additive inverse of A, and A minus B really means A plus the additive inverse of B. And in particular, the special case where B is 0, the additive identity, A plus H equals H, if and only if A is an element of H, which is true if and only if negative A is an element of H. In the special case where B is 0. So you can think about these facts that these things are true, actually without thinking about ideals. You could think about these kinds of things even if H was just a subring, but then the factor ring could not be made. Multiplication would not be well defined. But we're not really talking about multiplying elements of the factor ring here. We're just talking about equality of cosets. So coming back here, this thing, because it's an I, can get sucked into it. This expression, this matrix plus I can be just replaced by I effectively. Another way to look at this is to wonder, you know, the book is claiming here that 7, 8, 5, -3 plus I equals 1, 0, 1, 1 plus I. Are those cosets really the same? That's what the book is claiming in the calculation. Well, just think about this condition. If I subtract these two matrices, is it an element of I? Yes. Since 7, 8, 5, -3 minus 1, 0, 1, 1 equals 6, 8, 4, -4, and that has all even entries. That's an element of I. In a sense, when we are confronted with a problem like this, in doing this calculation, we're thinking about a left coset, an element of the factor ring, and we're trying to find the simplest coset representative. And in this case, it's 1, 0, 0, 1, 0, 1, 1. Try another example quick. Factor ring. 17, -15, 14, 13 plus I. What element of the factor ring is that? What's the simplest coset representative? Do what the book does. Rewrite this matrix here as the sum of two matrices, one of which has only zeros and ones, and one of which has only even entries. And the ones are going to have to occur in the same spots as the odd numbers, and the zero occurs in the same spots as the even numbers. And then I just have to figure out what matrix goes here. This would have to be a 16 here, a -16 here, 14 and 12. But then that gets sucked in. And we see that this left coset and this left coset are the same. They are the same element of the factor ring. That's the simplest coset representative of this particular element of the factor ring. It gets even more fun. Example 11 is even more fun. Example 11. More fun, perhaps, even more confusing when you first read it. Did you read this? Were you confused? It's kind of confusing. You get weird looking statements like 2 equals I in there. What is the author talking about? 4 equals -1. It's some sort of modular arithmetic, but it also involves the imaginary unit I somehow. Remember, Zi is the Gaussian integers. All complex numbers of the form a plus bi, where a and b are integers. And I is the imaginary unit, the square root of -1. It's a ring, commutative ring with unity. One can be thought of as 1 plus 0i. In fact, it's a subring of the complex numbers. Is it an ideal on the complex numbers? I'll let you think about that. The answer is no. It would be this Zi, the plain Zi would be a subring of the complex numbers. That's not an ideal. I'll let you think about why. However, if I ignore all of C, the complex numbers, and just focus on Zi as being my big ring, and think about an element in there, I can form the principal ideal generated by that element. That's what this symbol means. And that will be an ideal. We verified that. That was example 3. That principal ideals are indeed ideals. The name makes sense. And so I can form the factor ring under coset addition and multiplication. I guess I haven't written those down. The general coset addition is the same as in group theory. I'll call the ideal capital A because that's what the book often does. To add two cosets, you add their representatives. To multiply two cosets, in the factor ring, you multiply their representatives. And again, the key thing to showing this is well defined, the second case is that A is an ideal in R. That if you had different coset representatives, you get the same coset in the product. That's the goal, is to show that. Make sure you read and understand that proof. What does this ring look like? Of course, the elements are of this form. Think about it. They're left cosets because it's a factor ring. An arbitrary ring element in Zi plus your ideal is an arbitrary looking left coset. But just as in example 10, we might be after trying to find the simplest elements of cosets. That might be one goal. What do distinct cosets look like? 2 minus I, the element 2 minus I plus the ideal, the principal ideal generated by 2 minus I, this left coset equals this. Why? Because 2 minus I is in the principal ideal generated by 2 minus I. That's why. It's that fact right there. H is the same as 0 plus H. And this means that when dealing with coset representatives, we may treat 2 minus I as equivalent to 0. In other words, 2 equals I. What is the author really saying then? Does 2 really equal I? No, it doesn't. Not in the complex numbers. 2 and I are certainly different numbers. Think of it this way. So we've said 2 minus I plus the principal ideal generated by 2 minus I equals 0 plus the principal ideal generated by 2 minus I. I could, for example, add the coset I plus the principal ideal generated by 2 minus I to both sides of this. And addition is commutative, so it doesn't matter which side I put these things on. And if I do that, remember how I add cosets, it's right up here. I add the representatives. So when I do the addition over here, I add the representatives and I keep the ideal the same. I get I plus 2 minus I plus the ideal, that left coset. And over here, I add the representatives as well. I add 0 and I, 0 plus I. But this simplifies, the i's cancel to 2. And this simplifies to I. So we have this truth, this left coset equals this left coset. I and 2 are both representatives of the same left coset. That's what the author means, really, when the author says 2 equals I in this factor ring. That's really what the author means. We're just sort of ignoring the ideal when saying that, because it's always the same. When you're working in this factor ring, the ideal that you put there is always the same. So maybe we should just ignore it sometimes for sake of convenience. The author then goes on to claim that 2 equals I implies by squaring both sides that 4 equals -1. Because 2 squared is 4 and I squared is -1. But what's the author really doing when they say that? Really working with coset representatives. Again, the fact that this is true means if I square both sides, I've got to get the same thing. Squaring in the factor ring. But how do you square a factor ring element, a coset? Well, the squaring is a multiplication. You got to multiply the representatives. But if I'm squaring this one, I've got the same representatives in both factors. 2. 2 squared is 4. This is 4 plus the ideal. Same kind of thing over here. When you multiply cosets, you multiply the representatives. I times I is I squared, or -1. So that's why 4 equals -1. More precisely, this left coset equals that left coset. 4 and -1 are 2 representatives of the same coset. Hanging with me here? It's a lot to take in. Let me show you one other thing about this example that's kind of cool. What does it mean for a given left coset of the form a+bi plus the ideal to be the identity ideal? 0 plus the ideal, or if you just prefer, you can just write the ideal itself. What does it mean? When would this be true? Is my question. What is this equivalent to without thinking about factor rings? Well, just as we had mentioned a number of times today, that's going to be true. A plus I h equals h if and only if a is an element of h. In the context of this example, this is going to be true if and only if a plus bi is an element of this principal ideal. But when is that true? What does that mean? Well, you got to go back to the definition of a principal ideal. That right there. All ring multiples of A. In this case, all ring multiples of 2 minus I. So this is equivalent to saying A plus BI equals, I don't know, call it C plus DI times 2 minus I for some integers C and D. Let's try to see if we can work out what this is equivalent to. Expand this out, multiply these two complex numbers. The real part is going to come from the F and the L of FOIL. First times first is 2C. Last times last is D times negative I, which is negative DI squared. But I squared is -1. Negative D times -1 is positive D. And outside times outside and inside times inside both involve an I. Negative C times I and positive 2D times I. So this is equivalent to saying the following system of equations is true. A equals 2C plus D and B equals negative C plus 2D for some integers C and D. Now, such a system of equations, if we wanted to solve for C and D, would definitely always have a solution if we allowed C and D to be real numbers, or even rational numbers for that matter. However, we're restricting C and D to being integers. And that means this won't necessarily in general have a solution for arbitrary A and B. They have to be special A's and B's for this to have integer solutions for C and D. Let's think about linear algebra here in vectors. This is equivalent to saying the vector AB, writing as a column vector, is equal to C times the vector 2, -1 plus D times the vector 1, 2 for some integers C and D. And this can be imagined geometrically. Draw these two vectors as arrows in the plane. Two, -1, right about here. 1, 2 goes about like this. These are going to be at right angles to each other. They're going to be orthogonal. It would form an orthogonal basis for the plane under as a vector space, though you'd have to allow real scalars in that case. What does it mean for a vector AB to be a linear combination like this where C and D are integers? If you make a grid based on these basis vectors, so to speak, that would look about like this. So it's like I'm making graph paper that's sideways, something about like this, and continue it forever in all directions. These lattice points would be the elements a plus bi that satisfy all these things, where this is true ultimately. And this lattice does happen to include, and by the way, those points all have integer coordinates because these two have integer coordinates. And this includes this point right there, which happens to be the number 5, or 5 plus 0i. Which is equivalent to saying 5 equals 0, like they do here. For the sake of time, I'm not going to finish this example today, but there's more calculations you should think about. I would encourage you to think about this picture some more. And essentially, all these dots put together as a set forms the trivial coset with representative 0. There's 0 right there. Here's 2 minus I right there. Here's 5. You might wonder where are the other cosets? You might try to make a pretty drawing, maybe with a bunch of different colors, showing you the points in the other cosets. There's in fact only 5 cosets total. This ring is isomorphic to Z5. In fact, it's a field, since 5 is prime. For our last 9 minutes, let's look at example 12. Let Rx denote the ring of polynomials. We've seen that notation before with real coefficients. So the fact that there's an X in the square brackets means it's a ring of polynomials. Standard notation. Whatever ring is there, whether it's Z or R or maybe Z2 or Z3 or whatever ring we want, are the coefficients. We do typically want it to be a commutative ring here. We want the coefficients to come from a commutative ring, and typically with unity. And that would rule out having polynomials with matrix coefficients, wouldn't it? Since matrix rings are not commutative. So you might wonder, could I still consider polynomial rings with non-commutative coefficients? So I could have a polynomial with matrix coefficients? Maybe. I'll let you think about that, but we don't do that in this book. Consider this principal ideal domain, the principal ideal generated by x squared plus 1. As an ideal, not a subgroup, not a cyclic subgroup. In fact, whereas I said 20 some minutes ago, in Z, the integers, principal ideals, and cyclic subgroups do end up being the same. Here they definitely would not be the same. If you were thinking of this as the cyclic subgroup generated by x squared plus 1, it would be all polynomials that you could form by adding this to itself any number of times, or 0 times, or adding its additive inverse to itself an arbitrary number of times. In other words, the cyclic subgroup generated by that thing would be all polynomials of the form nx squared plus n, where n is an integer. That would be the cyclic subgroup generated by the single polynomial x squared plus 1. But the principal ideal generated by this is not just those polynomials. I got to multiply this by an arbitrary polynomial in here. What kinds of polynomials can I get by multiplying x squared plus 1 by arbitrary polynomials in here? Or maybe another question you could ask is, what polynomials can I not get? Except for 0, I certainly could not get any constant polynomials. Except for 0. I could multiply this by 0. There's no polynomial you can multiply x squared plus 1 by to get a non-zero constant polynomial. You can't multiply by 1 over x squared plus 1 because that's not a polynomial. In fact, you can't get any non-trivial linear polynomials either. Ax plus b. Because there's no way when you multiply this by a non-zero polynomial that the degree is going to go down. What you're really going to get is you're going to get all polynomials p of x that can be factored in the form x squared plus 1 for some polynomial q of x. That's what you really get. To be more specific, I could say the set of all polynomials p of x such that p of x equals x squared plus 1 times q of x for some polynomial q of x. Q of x in Rx. By the way, don't be bothered by the fact that we use square brackets there and parentheses there. It's just tradition. There's actually another meaning when you use parentheses here that I'll talk about later. Just go with the notation, even though it's weird. That's what you get. All polynomials such that when you divide by x squared plus 1, you get a remainder of 0 when you do long division. And in general, you do have to do long division, not synthetic division, because synthetic division only works when you divide by linear polynomials. So in general, you do have to do a long division. So it's a principal ideal generated by x squared plus 1. It's certainly an ideal. In fact, yeah, it's a principal ideal. We talked about proving principal ideals of this form are indeed ideals. Therefore, we can form the factor ring. Here, the book is emphasizing exactly what I just emphasized a minute ago about what this ideal is. Here's the factor ring, and the claim is, here's the more general form for cosets, g of x plus the ideal, g of x being your arbitrary representative, g of x possibly being a very high degree polynomial, you know, 1,000,000 degree or something. But the claim is that you can find simple coset representatives. You can find linear coset representatives for any g of x. 1,000,000 degree, billion degree, Google degree, whatever. Any g of x polynomial, you can find integers, or excuse me, real numbers a and b to say that that left coset equals this left coset. How? Well, in theory, well, in practice, you do long division. You actually do long division to find the coset representative. In the theory, to prove it, you'd have to say, well, I know by the division algorithm for polynomials, which we actually haven't talked about yet. We talked about a division algorithm for integers. There is also a division algorithm for polynomials. It's in a later chapter here, chapter 16. But effectively, that's what this is saying. We can write g of x as x squared plus 1 plus a quotient that I get from doing the long division, and I would put it at the top of the long division, plus a remainder that I'd be at the very bottom of my long division. And since I'm dividing by a quadratic, it turns out the remainder would have to be a lower degree. Just like when you divide numbers, 17 divided by 5 is 3 with a remainder of 2, right? 17 divided by 5. 5 goes into 17 3 times with the remainder of 2. The remainder has to be less than what you divide by. 2 is less than 5. Similar kind of thing here. The remainder here, the degree of the remainder has to be smaller than what you're dividing by x squared plus 1. So it's got to be a linear polynomial. Again, for some technicalities, I really shouldn't quite say it that way because the zero polynomial technically has a degree that's undefined, and the author kind of hints at that here. The author says either r of x is the zero polynomial or the degree is less than 2. Either way, it's a linear polynomial, ax plus b for some real numbers a and b. And what happens to say that we can ultimately get this is when you look at this expression, you should think of the q of x times x squared plus 1 as getting sucked into the ideal. Why? It's because it's a multiple of x squared plus 1. It's an element of this ideal. The r of x is not, so it just stays in front. But it is linear, and therefore we can say this is true. How is multiplication done? X squared plus 1 is in the principal ideal generated by x squared plus 1, and therefore in this factor ring, it's equivalent to 0. And therefore, x squared is equivalent to -1. And so instead of doing long division, it's more fun to do this. What's the author doing there? Multiplying these two factor ring elements. Notice you multiply, first of all, the representatives. X plus 3 times 2x plus 5. If you use FOIL, it gives you 2x squared plus 11x plus 15. Check it in your mind for a few seconds here. X times 2x is 2x squared. 5 times x plus 6 times x is 11x. And then 3 times 5 is 15. But then we can simplify to this. Why? Replace the x squared with -1. That's how. Seems really confusing because when would we ever replace a variable squared with a number? Well, we do in this factor ring. If you replace x squared there with -1, you get -2. -2 plus 15 is 13. Done. We're out of time. You can do this for higher degree polynomials as well. You could replace x cubed with -1 times x. You could replace x to the 4th with -1 squared, which is +1. Any x to the 4th could be replaced with +1. The rest of the chapter is still plenty hard, but it's plenty important. Make sure you really study prime ideals and maximal ideals and think about examples, and then get into chapters 15 and 16 as well. Have a good day.